Cool. We're back. We're coming to the end of like at least the math for this project. Of like getting through predicting things. Like saying here's the motion, here's what's causing the motion. Any ideas on what that tells you? I know I've asked this a couple of times, but why go through all of this? Like, why would you want to know a solution to a differential equation for these design problems? Has anyone thought about that anymore? It's all you can think about. Why would I do this? But keep it in mind as you're kind of going through this, like what we're doing, why we're doing it. So last time we left off with the last part of like some kind of frictional stopper where we have rough walls or maybe like rubber walls or something that are trying to stop this object. And we came up with this equation of motion that mass times acceleration is weight minus that force of gravity, that force of friction. Do we know anything about acceleration from this equation of motion? Even if we don't know what normal force is. Because right now we don't know what that is, at least. Or maybe you do. Maybe you already know. It's 3, obviously. Take a second. What do we know about acceleration? And then also from, like, if we know something about the acceleration, what do we know about, like, position, velocity? Like those terms. Take a second, you can talk to each other, kind of brainstorm, but what do we know from this equation of motion? Yeah, acceleration is gravity, right? If there's no normal force, it's falling. Okay. Okay. What do you think? Oh, okay, like what do we know about acceleration from this equation of motion? It slows down. Okay. Do we know that it's going to slow down? Assume. Okay. Yeah. Yeah, friction usually slows it down. Okay. Yeah.
That just depends on the coefficient of friction.
Okay. That one, so the coefficient is giving us like 1/2. Oh, it depends on the velocity. What is the velocity of it? Oh, I thought you said velocity. What did you say?
I mean, if it's 1/2, and you bring in like the mass and the gravity friction,
Mm-hmm.
then you can slow it down.
Okay. Oh, if it's slowing down, so maybe slowing down. Yeah, that's what we have so far. Okay, nice. Yeah. Okay. Probably not gonna be fancy, right? Yeah, it just could be weird to like slide.
We'll stop that.
Jiggle? Okay. feels like it's gonna slow down. There's friction. Welcome. Thanks for joining. Okay. So, general feeling is that friction means slow down, that it's got to slow down. So initially we're doing 3 meters per second. This N, I mean, it's kind of an unknown right now. Like, we don't know what that normal force is. So we could look at some extreme cases. So let's say N is 0. No free will, yeah. If N is 0, how fast are we accelerating through our brakes, through our stopper? G, right? Like, we're just, it's the worst case scenario. Like, we didn't apply any force, so friction has no effect. Kind of like, not great. What would happen to V? Like, what's our velocity then? It's our original, like, 3 meters per second, like when we got to it, and then plus GT. So in that case, like, this thing is not going to slow down. What's the bare minimum where it at least, what would be another thing that we could take a look at? Like, what's another? We could just randomly plug in numbers, right? Like, the numbers aren't going to hurt us. We could say N is 100 and then figure out what is acceleration. What's another kind of limiting case? Or like edge case, yeah. Oh, it drops and like, oh, that it just can't move, yeah. Yeah, so there should be a case where like as it drops in, it just immediately stops, like right at there. It doesn't move through it, there's just sticks to the thing and there's no motion. Would that need big normal force, small normal force? Like, how much? Yeah. Sorry? If it's infinite, let's try that. What would that one look like? So if N is infinity, my 7-year-old like loves the idea of infinity right now. And I can't stop talking about infinity, and he's like, "What's bigger, infinity or 2 times infinity?" And like, they're equal. It's like, what? But so we've got infinite normal force, just as big as you can possibly make it, plus an extra 10 pounds, and then add an extra 10 pounds to that. What does that do to acceleration? negative infinity. Yeah, because that mg compared to infinity is nothing. Like it doesn't matter that it's there. So then this would be a 3 minus infinity times t. Does velocity go to negative infinity? Yeah.
It would have to go to zero because velocity, the block would go upwards. due
The
to-
block can't go
due to
upwards,
friction.
but we said acceleration is negative infinity. Why doesn't it keep? I agree. Like, just intuition wise, it doesn't make sense that it's. So there's something weird about our equation of motion, right? Like, it's not. When you stop moving, when you hit zero velocity, friction stops working, if that makes sense. Like, you can't have dynamic sliding friction unless you're actually sliding. Like, you have to be moving for the thing to work. And same thing, if we change directions, like if there was a spring to push us back up, then friction doesn't continue to act however you entered the brake. It would flip directions. So we would reach zero speed in infinitely small time, or really, really big, really small, something like that. Let me get rid of this. Cool. So really what we're kind of figuring out is that our velocity is going to decrease, and then once it hits that 0 point, it's not going to change anymore. We can't use friction to, like, yeah, at least in this case where it's trying to slide through our brakes. You can roll, like technically when you drive a car, friction is the force pushing you forward. But okay, cool. And in this case, we figured out that this slope is a negative infinity, so it'll hit zero, infinitely small. So now, choosing a normal force, like what do we know about acceleration here? Is there anything that we can say about it? Is it a function of position? Not directly, right? Is it a function of velocity? I see some head nods. A little bit? No? Thinking about it? Yeah.
It's the friction, right? It's sort of a function of velocity. Like if the velocity is zero, it's not zero, it's a different number. Velocity is not a different number.
Yeah, so it is like kind of a function of velocity, but as over this small interval for positive velocity, it's a number, right? Like it's some 2 mu n number. So the nice part is that it's for this interval, for the interval that we care about, from going initial speed to zero, we have constant force. And what's a constant force mean for acceleration? acceleration's constant. Yeah, F is ma, F is constant, a is constant. At least if we don't have any nuclear things happening and mass is changing. But we don't have that because we're dealing with dynamics, so we're not dealing with nuclear fission or fusion. So if A is a constant, then those kinematic like equations, yeah, the kinematic equations hold true. We don't need to go through like differential equations or anything. We have an extra term in there, that normal force, so we can play around with, but we don't need like diffie-q to solve this problem, which is kind of nice. Nice to skip a little bit of math along the way. Cool. All right, what else do you want to try? Give it a shot. We know what the kinematic equations are. I think we do. Probably have nightmares about them, but we can write them down. So we've got like math in there. How much force do we need? How big of an n should we have? Do we just want infinite n and stop this thing immediately? I don't know. What do you think? Try it. Like you could try something, you could talk about it. Like where do we go from here? I would just try to stop it immediately. Okay. Yeah. Because now we have the option, right? We can clamp it as hard as we want. What do you think? Where do we go from here? Find the end. Okay. Yeah. Do we want to use to find the end? Not sure. Okay. Yeah. Oh, what happens there? A is 0. Okay. Yeah. Yeah. That's kind of our minimum, right? So there should be some cutoff case, right? Because we had, if n is 0, then it just keeps accelerating at g. If n is negative, if n is positive infinity, then we have negative infinite. So at some point, there's some crossover where we go from like a positive downward acceleration to a negative kind of upward, like actually slowing down. What is that cutoff? When does a equal 0?
When n is equal to mg divided by 2 mu.
Similar idea. Oh yeah, mg over 2 mu,
Yeah.
like that. what do we have for that value? How big is that n? Is that a big number, a small number? How big of a normal force do we need for that one?
Well,
0.981. How does that sound? Almost one Newton. How big is 1 Newton? Does anyone know? Like how much that is? You didn't set your bathroom scales to Newtons, like true engineering nerds. Like, haha, you can set any metric unit I want. Roughly like 4 Newtons per pound, right? So a quarter pound. That's pretty easy. We should be able to find a way to get like a quarter pound of pressure of this pushing on this thing. So that's doable. Does it stop it though? Does it slow it down? No? Okay, yeah, so it's moving through. It's no longer accelerating, but it's also not slowing down. So anything bigger than this should slow down. So today's quiet. Because it's just waiting for, like, hoping the answer is just like given, like, here's the answer. I don't know. What do we do next? Yeah.
Maybe you find an acceleration of like the velocity zero.
So we need some kind of acceleration that brings it to 0. Okay. Do we have any criteria for like when or where it needs to get to 0? Because that would help kind of confine the problem, right? Because really, if we just had like 0.99, it should be enough. Or even 1 Newton. It's enough. It'll slow it down. Yeah. So if we think about this in terms of like, we only have a 0.1 kilogram object. If we need 10 meters of rubber to slow it down, and it's only moving 3 meters per second, like this is something that you could catch with a baseball glove. So it seems weird to design something that's like really big for such a small little like piece of a manufacturing or an assembly line or something. All right, so you can choose whatever you want, whatever you think is small. What about time-wise? what's the benefit of taking a longer time to stop?
More gradual acceleration.
Gradual, yeah, so things are happening slower. Yeah. Yeah. Yeah, like if this was like an egg drop sort of thing, like trying to stop an egg, then you're kind of limited by how fragile the egg is, like how much force you can apply to it. So even just the side normal force, like how big can that normal force be? Yeah. Do you remember what impulse is? Have you heard that term before? What's an impulse on an object? Not like a biological impulse of like the object wants to reproduce, so it's like trying to talk to other objects and like see how they're vibing. But like mechanical impulse. Ha! Yeah. Yeah, so impulse is change in momentum. So if you have a change in momentum, which is exactly what we have here, it's moving and we're going to stop it. So it's going from motion to no motion. So total impulse, and I'm kind of writing it down, one as a reminder, and then two just to kind of see how this thing works. We're doing 3 meters per second. We come into our system. That system applies a force for a given amount of time, and that total impulse has to be 1/3 of a Newton second. Does that limit how much force is applied? Like we can only have a certain amount of force for this impulse? So one example, if it takes 1 second to stop, how much force was there? .31, yeah, 0.31. Now, if it takes half a second to stop, did the force increase or decrease? Increases, right? Like, because the total stopping impulse has to be the amount of momentum that we're taking away. So that if we're looking for like how much force are we actually applying to this object, this is a good way to figure that out. Like, hey, F delta T is 0.3. The smaller delta T gets, the bigger that F becomes. So when we said we had an infinite normal force and an infinite like acceleration, now delta T is 0, so how big of a force did we apply to our object? Pretty darn big. 8. But sleepy 8. Yeah, infinite. We have like infinite force for infinitely small time. It's like a Dirac delta function. Have you seen those yet? No? Just wait. It's going to be so great. Dirac deltas. there's 0 everywhere, except for exactly when you hit something when they go to infinity, and then come back. And then come back to 0, the Dirac delta. So that's what it would, like, the force. And normally it's just like really big, right? Like it's not an actual infinite force for an infinitely small period of time, but. I don't know. Yeah. Take it from there. Let's take like 2 minutes. Where do you want to go from there? We have a few different approaches. You can use them all. You could use one. You could plug something in and just say, this is it. This is the answer. I don't know. Wherever you want to go from there. Like two minutes. Plug something in. See where you want to go. You don't have to do it alone. It's all group projects. You can share what you're thinking. So in order for this thing to stop, we need a normal force. The question is like how big a normal force do you want to put in Yeah, it's kind of both directions. You're applying for this way and stopping it that way. So the bigger the force, the quicker you stop, so also the more stress you put on. Okay. Lost with the math that we're doing, or with the idea of the math. Okay. So in this one, it's open-ended. Normal force can be whatever you want it to be. It's not going to change the physics that are happening. The only thing that changes is how long and how far the thing goes. And that's kind of what we're trying there. That's not there. If there's no normal force, then there's breaking. And it's infinite. It'll stop it. It will not be any force. Both directions. Yeah, I mean, you can start with just like, hey, we need to try this one. See how far it goes. Either say, yep, I did it. No, we change it. Let me double up because I want to be You could try that, yeah. But I like the thought process of like, no, I want it to slow down, I want negative. But in this case, we have positive 3.1 that we want to push this way to turn it into 0. So the more negative our acceleration is, the faster we go. Oh, because I wrote a negative there? Or, oh, well, it should just be a t squared too. So it's going to be like yeah. And then for the last, just a.
Oh, were you just saying that you wanted to be negative, so if you didn't just
Yeah.
Oh, I was thinking that as like if you
That's true. Yeah, two negatives would be a positive. Yeah, that's true.
Okay.
really don't like open-ended problems. That's what I'm discovering after this little experiment. Like, just tell us what the normal force is, and then I can give you what you want. I'm like, that's up to you. Like, it's fine. It's not like a creative writing assignment where you need like character names and arcs and stuff. It's one number. You're coming up with one number. And this is probably 90% of your job as soon as you leave school, is making up these numbers. Like, and you gotta come up with numbers that make sense. Because if you walk into the meeting and you're like, okay, we're building this brake, and all we need is 6,000 pounds of normal force so that we can stop this iPhone as it gets from one system to another. You're gonna be like, why do we need a hydraulic press for this braking system? And what's gonna happen to these phones? Like, you raise a lot of questions. And people were the questions that came up as I was walking around was like, how do we do this? How do we figure it out? One way is just keep filling out this table, right? Like, we started making a table of like, here's n is 0. We have no effect. G just keeps increasing. We have an n is infinity, where it's infinite effect, but also infinite damage. And then we have the case where A is 0, where we solved for when this thing kind of hits that like steady state, like it's constant velocity going through it. You could just keep plugging in numbers, right? Like try a 2, try a 3, try a 10. The other way is, since we know these kinematic equations, and then we even have this one, right? The one that everybody forgets. We could solve for what is the acceleration that we need to get delta x to be like 10 centimeters or something, or 5 centimeters, whatever your number kind of makes sense to you. Doesn't. Oh, I'm drawing it underneath my head. Dealer's choice, delta x. So whether you're trying to say like, here's the time that I want, and we even found like impulse, we could say how much force we want to apply for a given amount of time, all that. It's like fair game. You could even figure out acceleration, because usually there's limits on like shipping things. So have you ever seen those like things that say like your box has been damaged during shipping? It's a little like beaker. It should be white, but if it's red, that means like an Amazon driver just like hucked it into your driveway, maybe kicked it as well. But you could figure out like what is that number there. I think usually it's like 2 G's. So anything more than like 20 meters per second squared is probably gonna break whatever you're dealing with. It might even be like 1.2 or something, like a G plus a little. So you could solve for A and then go with like, hey, in order to limit this to acceptable manufacturing specs, we need to keep A here, which means it'll take this long and this distance to stop it. Is that okay? You have some parameters in the playground. It's only a little sandbox that you're playing in. It's not, you're not out in the world doing whatever you want. Cool. All right, next time we'll come together more like group work next time. So we did a lot of like math kind of guided math together, like talking through the physics, introducing equations. Next time is like the wrap up, like what are you doing with this information? Why is it important? What are you reporting? What graphs do you want? And all of that. Okay, cool. Thanks a lot.